Let's open for questions.
So we have had a couple of questions in the chat already. So I would say, Ronan, you want to start asking your question?
Yeah. So the problem of this programming model is that it's very difficult to fit it in existing languages. And it's also very complex to implement it in compiler infrastructure such as Clang LLVM. So I've not seen a strong motivation for this and a strong use case. So can you elaborate about that?
For the scalable use case?
Yes.
Well, okay. So I think in HPC you might be right, but if you look beyond HPC to other places that ARM works in, and there's a limit to how much I can talk about here because I can't talk about kind of future calls and what our partners are going to be doing and so on. But Android, for example, is a very important market for ARM, and I cannot imagine Google allowing individual builds for all micro architectures that people use for their mobile phones and for kind of clamshell devices and things like that that run on Android. So there are spaces outside of HPC where you cannot rely on users stating at compile time what the vector width is going to be, but for whom vectorized code is important and will become more important.
Yeah,
very nice. Yeah. So Sven, you had a question, or was it just a comment? You want to say it out loud?
I first had a follow-up comment to Ronan's comment about sort of how much performance could you potentially gain from assuming something about the implementation. Let's say that you intentionally build in the context of HPC, you intentionally do a build that is fitting a certain implementation, and for example, you could have a exit clause at the beginning of the process. You're checking, are my assumptions correct with respect to the currently used hardware, and then say, sorry, you're running on the wrong machine or something like that. Is it possible to estimate how much performance can be gained from not having to assume a variable vector length?
It's really hard when you've only got one implementation so far. but okay, that's a little bit flippant. There are, if we think about it in terms of capabilities, then for general auto vectorization, so in particular loop vectorization, then with work there should be very few reasons why a width agnostic implementation of a vector loop should not be as performant as a width specific vectorization of the same loop. There is nothing I know of that would ever make it faster. So the best you can do is parity. But there aren't any fundamental reasons, and this depends on microarchitecture a little bit, but there shouldn't be fundamental reasons why that can't be the same. There are exceptions to that in terms of capabilities, such as SLP vectorization. So if that's super important for your workload, then it's either very hard or impossible, I'm not sure which, to write SLP vectorization in a width agnostic way. And so what you would probably end up doing is having potentially multiple implementations of an SLP vectorized piece of code with iPhones or similar to work out at runtime, which is the appropriate one. Again, it's all work. So I think the challenge here is less to do with fundamental capabilities of the architecture to be as performance, but the width-specific vectorization is from a much more mature starting point.
Okay. Simon?
Hi, Will. So I suppose you're talking about the vector predication extension for LVM as the community effort. So is ARM planning to contribute to that in any way?
I do not have an active plan to contribute to that in any way at the moment. Sorry, Simon, I imagine that's not the answer you want. As ever, the difficulty here for us is one of prioritization, and the need for us, certainly for our commercial compiler, for having perfect support for IEEE floating point exception handling and so on, isn't a sufficiently overridingly important use case to concentrate on that, as opposed to, for example, getting base SV support in and improving the loop auto-vectorizer.
But you will need a predicated reduction operators, right?
We will need to be able to support reductions for sure. Whether or not that, if we guard the, I'm just trying to think if I'm answering the wrong question, and why that wouldn't work with what we have today. So we certainly downstream are able to vectorize predicated loops that contain conditional code. Is that the use case you're thinking of, or is that something else?
I'm thinking about reduction operators, say a add reduction, for example, on a vector. So the vector is reduced to a scalar, but you only want to consider certain lanes.
Yes.
No support for that right now.
Okay. Yes. We would need to be able to support that. Now, you're demonstrating my ignorance of the detail of LLVM right now in not understanding the state of that in upstream versus what we have downstream. I know we can do that fine downstream, and I don't know why there's a difference there. So I'm going to have to defer a strong statement about that, I'm afraid.
How is a loop with a body containing math library called sine cosine handled with SVE?
So in the downstream compiler, and I think in upstream LLVM now also, we have the ABI that was the vector ABI that was developed initially by Intel, that we worked with Intel on, that allows a library to describe the size and shape of a vector argument, and that supports the idea of that's been extended to support the idea of scalable vectors, and so you can declare functions, so vectorized functions, as having a certain size and shape of arguments, and of being a vector implementation of a given scalar function. And then then there's also support for the auto-vectorizer to recognize that you have a scalar call within a loop, and that call can be vectorized by replacing it with the appropriate vector call, and that just works fine. That I think is supported both upstream and downstream. So our compiler does this, and we ship vector implementations of basic math routines and so on, and the auto-vectorizer picks those up and uses them. We have open sourced, so we've worked with the open source sleeve library in the past, which supports SVE, and you can build SVE capable libraries for basic math routines. And we also have an optimized set of math routines for both scalar and I think now vector in there as well, called ARM optimized routines, which is on GitHub, from which our own downstream commercial math libraries are based. So this is well supported today, and it works.
One more question, and then we have to stop this. Sven, you had a question?
Yeah, I have a bit of a question about the workflow internally at ARM. You may or may not be able to answer that. So my question really is on if I look at the work my students has been doing in vectorization, if you really want to push hard on getting a large degree of vectorized code in your applications, the low-hanging fruits are quite easy, but you get into roadblocks in terms of semantics. You like to have this and that in particular specific memory operation and whatnot, right? So my question is, what kind of use cases are you using at ARM to drive development, or are you doing compiler, vectorizer, / hardware code design in order to figure out which operations to put in, assuming that you continue developing a new generations of SVs?
It's a great question. Making sure that the CPU designers, which of course with ARM is our internal CPU designers, so we design our own cores, which we call license, and is also our partners, because they design their own cores, and making sure that the code that they are using to decide how to design their microarchitectures and it is as representative as possible for the workloads within the domain that CPU is targeted as possible, is a really difficult chicken and egg problem, because if you're designing new extensions to the ARM architecture or any architecture, by definition, those won't be well supported in compilers yet. And if you're trying to make implementations of those, then you need a high quality optimized code from a very applicable workload in order to make a kind of a perfect CPU design. So so it follows from that it's really important that we work closely with the architecture team and with the microarchitecture teams to ensure that we find workloads that are as representative as possible and get high quality compiled implementations of those workloads. And which workloads we choose, though, is very, very dependent on domain. So I can imagine you can, I don't know that I'm allowed to share precisely which workloads we spend most of our time working on, but if you look at the people who are really interested in ARM today, then that's Fugaku, obviously, and the Department of Energy have shown a big interest. And then look at the workloads that they most care about, then those are the kind of things that we're typically focusing on. But in other domains outside of HPC, it's very different workloads. Does that answer your question, though?
Thank you. I think it does.
Thank you.
Okay, Will, thank you very much for your talk. It was great. We have a couple more questions in the chat. If you stick around and take a look at them, there might be some you might want to respond to privately or in the chat.
Sure,
feel free to do so.
I'll do that in the chat if I can. Sure.
Yes, we kind of ran out of time. I'm sorry about that.